This video is related to the Introduction Learning Unit of the Data Visualization Educational Module. Visualization is the communication of information using graphical representations. Pictures have been used as a mechanism for communication since before the formalization of written language. A single picture can contain a wealth of information and can be processed much more quickly than a comparable page of words. This is because image interpretation is performed in parallel within the human perceptual system, while the speed of text analysis is limited by the sequential process of reading. Pictures can also be independent of local language, as a graph or a map may be understood by a group of different people. Data visualization is part art and part science. The challenge is to get the art right without getting the science wrong and vice versa. A data visualization first and foremost has to accurately convey the data. It must not mislead or distort. If one number is twice as large as another, but in the visualization they look to be about the same, then the visualization is wrong. At the same time, a data visualization should be aesthetically pleasing. Good visual presentations tend to enhance the message of the visualization. If a figure contains jarring colors, imbalanced visual elements, or other features that distract, then the viewer will find it harder to inspect the figure and interpret it correctly. A primary goal of data visualization is to communicate information clearly and efficiently to users via the statistical graphics, plots, information graphics, tables, and charts selected. Effective visualization helps users in analyzing and reasoning about data and evidence. Therefore, it makes complex data more accessible, understandable, and usable. An excellent data visualization has specific qualities. Visually appealing, the advent of more sophisticated visual creation tools and the high quality of mobile apps have raised the bar very high on the user experience. Scalable, if a data visualization is successful, others will want to use and leverage it. It is a good practice to build the visualization on a system that's scalable for accessibility and for future maintenance and modifications. Provides the user the right information. It's a problem when users focus on the visual or a particular feature and not on what they really need. Before creating a visualization, define exactly how it will be used, such as for self-service, drill down, deep analysis, or executive overview. Accessible. An accessible visualization is easy to use and can be modified easily when necessary. Also, the data must be accessible on any device, at any time, at any place. This feature is critical to user adoption. Rapid development and deployment. Users need their visual information as soon as possible and therefore must be developed and provided in a timely fashion. Following previous discussion, it is somehow helpful to understand why visualization is a useful medium for examining, understanding and transmitting information. Visualization leverages the incredible capabilities and bandwidth of the visual system to move a huge amount of information into the brain very quickly. Visualization takes advantage of our brain's built-in software to identify patterns and communicate relationships and meaning. Visualization can inspire new questions and further exploration. Visualization helps identify sub-problems. Visualization is appropriate for identifying trends and outliers, discovering or searching for interesting or specific data points in a larger field. One way to classify a data visualization is by counting how many different data dimensions it represents. By this we mean the number of discrete types of information that are visually encoded in a diagram. For example, a simple line graph may show the price of a company's stock on different days, that's 2 data dimensions. If multiple companies are shown and therefore compared, there are now 3 dimensions. If trading volume per day is added to the graph, there are 4 as is shown in this figure. This count of the number of data dimensions can be described as the level of complexity of the visualization. As visualizations become more complex, they are more challenging to design well, and can be more difficult to learn from. For that reason, visualizations with no more than 3 or 4 dimensions of data are the most common, though visualizations with 6, 7, or more dimensions can be found. The term infographics is useful for referring to any visual representation of data that is manually drawn, specific to the data at hand, and therefore non-trivial to recreate with different data. Aesthetically rich and relatively data poor because each piece of information must be manually encoded. To put it another way, infographics are illustrations where the data representation is manually laid out or sketched, probably with appropriate drawing software such as Adobe Illustrator. Because of their manually drawn process of creation, infographics have the option of being aesthetically rich, as is shown in this figure. Another consequence of their manual origins is they tend to be limited in the amount of data they can convey, simply due to the practical limitations of manipulating many data points. Similarly, it is difficult to change or update the data in an infographic, as any changes must be implemented manually. By contrast, the terms data visualization and information visualization, informal, data viz and info viz, are useful for referring to any visual representation of data that is algorithmically drawn, easy to regenerate with different data, that is, the same form may be repurposed to represent different data sets with similar dimensions or characteristics. Often aesthetically barren, that is, data is not decorated. Relatively data rich. In general, large volumes of data are welcome and viable, in contrast to infographics. Data visualizations are initially designed by a human, but are then drawn algorithmically with graphing, charting, or diagramming software. The advantage of this approach is that it is relatively simple to update or regenerate the visualization with more or new data. While they may show great volumes of data, information visualizations are often less aesthetically rich than infographics. Generally speaking, there are 2 categories of data visualization: exploration and explanation. The 2 serve different purposes, and so there are tools and approaches that may be appropriate only for one and not the other. For this reason, it is important to understand the distinction, so that the user can be sure in using tools and approaches appropriate to the task at hand. Exploratory data visualizations are appropriate when you have a whole bunch of data and you're not sure what's in it. When you need to get a sense of what's inside your data set, translating it into a visual medium can help you quickly identify its features, including interesting curves, lines, trends, or anomalous outliers. Exploration is generally best done at a high level of granularity. There may be a whole lot of noise in your data, but if you oversimplify or strip out too much information, you could end up missing something important. This type of visualization is typically part of the data analysis phase and is used to find the story the data has to tell you. By contrast, explanatory data visualization is appropriate when you already know what the data has to say, and you are trying to tell that story to somebody else. It could be the head of a department, a grant committee, or the general public. Whoever the audience is, the story you are trying to tell or the answer you are trying to share is known to you at the outset, and therefore you can design to specifically accommodate and highlight that story. In other words, you'll need to make certain editorial decisions about which information stays in, and which is distracting or irrelevant and should come out. This is a process of selecting focused data that will support the story you are trying to tell. If exploratory data visualization is part of the data analysis phase, then explanatory data visualization is part of the presentation phase. Such a visualization may stand on its own, or may be part of a larger presentation, such as a speech, a newspaper article, or a report. In these scenarios, there is some supporting narrative, written or verbal, that further explains things. It's worth mentioning that there is also a kind of hybrid category, which involves a curated dataset that is nonetheless presented with the intention to allow some exploration on the reader's part. These visualizations are usually interactive via some kind of graphical interface that lets the reader choose and constrain certain parameters, thereby discovering whatever insights the dataset may have to offer. Whenever we visualize data, we take data values and convert them in a systematic and logical way into the visual elements that make up the final graphic. Even though there are many different types of data visualizations, and on first glance a scatter plot, a pie chart, and a heat map don't seem to have much in common, all these visualizations can be described with a common language that captures how data values are turned into blobs of ink on paper or colored pixels on screen. The key insight is that all data visualizations map data values into quantifiable features of the resulting graphic. We refer to these features as aesthetics. Aesthetics describe every aspect of a given graphical element. A few examples are provided in the figure in this slide. A critical component of every graphical element is of course its position, which describes where the element is located. In standard 2D graphics, we describe positions by an x and y value, but other coordinate systems and one- or three-dimensional visualizations are possible. Next, all graphical elements have a shape, a size, and a color. Finally, to the extent we are using lines to visualize data, these lines may have different widths or dot patterns. Beyond the examples shown in this figure, there are many other aesthetics we may encounter in a data visualization. For example, if we want to display text, we may have to specify font family, font face, and font size. In addition to continuous and discrete numerical values, data can come in the form of discrete categories, in the form of dates or times, and as text. When data is numerical, we also call it quantitative, and when it is categorical, we call it qualitative. Variables holding qualitative data are factors, and the different categories are called levels. A concrete example of the various types of data is depicted in this table. It shows the first few rows of a dataset providing the daily temperature normals, average daily temperatures over a 5-year window, for 4 city locations. This table contains 5 variables: month, day, location, station ID, and temperature in degrees Celsius. Month is an ordered factor, day is a discrete numerical value, location is an unordered factor, station ID is similarly an unordered factor, and temperature is a continuous numerical value. To map data values onto aesthetics, we need to specify which data values correspond to which specific aesthetics values. For example, if our graphic has an x-axis, then we need to specify which data values fall onto particular positions along this axis. Similarly, we may need to specify which data values are represented by particular shapes or colors. This mapping between data values and aesthetics values is created via scales. A scale defines a unique mapping between data and aesthetics. Importantly, a scale must be 1-to-1, such that for each specific data value there is exactly one aesthetics value and vice versa. If a scale isn't 1-to-1, then the data visualization becomes ambiguous. In this figure, the numbers 1 through 4 have been mapped onto a position, a shape, and a color scale. For each scale, each number corresponds to a unique position, shape, or color, and vice versa. Let's put things into practice. We can expand the dataset shown previously, map temperature onto the y-axis, day of the year onto the x-axis, location onto color, and visualize this aesthetics with solid lines. The result in Figure A is a standard line plot showing the temperature normals at the 4 city locations as they change during the year. Figure A is a fairly standard visualization for a temperature curve and likely the visualization most data scientists would intuitively choose first. However, it is up to us which variables we map onto which scales. For example, instead of mapping temperature onto the y-axis and location onto color, we can do the opposite. Because now the key variable of interest, temperature, is shown as color, we need to show sufficiently large colored areas for the color to convey useful information. Therefore, for the visualization in Figure B, squares are used instead of lines, one for each month and location, and have colored them by the average temperature normal for each month. Just to emphasize that Figure B uses two position scales, month along the x-axis and location along the y-axis, but neither is a continuous scale. Month is an ordered factor with 12 levels and location is an unordered factor with 4 levels. Therefore, the two position scales are both discrete. For discrete position scales, we generally place the different levels of the factor at an equal spacing along the axis. If the factor is ordered, as is here the case for month, then the levels need to be placed in the appropriate order. If the factor is unordered, as is here the case for location, then the order is arbitrary, and we can choose any order we want. Both figures A and B used 3 scales in total, 2 position scales and 1 color scale. This is a typical number of scales for a basic visualization, but we can use more than 3 scales at once. To make any sort of data visualization, we need to define position scales, which determine where in a graphic different data values are located. We cannot visualize data without placing different data points at different locations, even if we just arrange them next to each other along a line. The combination of a set of position scales and their relative geometric arrangement is called a coordinate system. The most widely used coordinate system for data visualization is the 2D Cartesian coordinate system, where each location is uniquely specified by an x and a y value. The x and y axes run orthogonally to each other, and data values are placed in an even spacing along both axes as shown in this figure. The two axes are continuous position scales, and they can represent both positive and negative real numbers. To fully specify the coordinate system, we need to specify the range of numbers each axis covers. In this figure the x-axis runs from -2.2 to 3.2 and the y-axis runs from -2.2 to 2.2. Any data values between these axis limits are placed at the respective location in the plot. Any data values outside the axis limits are discarded. Data values usually aren't just numbers, however. They come with units. For example, if we're measuring temperature, the values may be measured in degrees Celsius or Fahrenheit. Similarly, if we're measuring distance, the values may be measured in kilometers or miles, and if we're measuring time, the values may be measured in seconds, minutes, or hours. There are 3 fundamental use cases for color in data visualizations. A. We can use color to distinguish groups of data from each other. B. We can use color to represent data values, and C. We can use color to highlight. The types of colors we use and the way in which we use them are quite different for these 3 cases. Color as tool to distinguish. We frequently use color as a means to distinguish discrete items or groups that do not have an intrinsic order, such as different countries on a map or different manufacturers of a certain product. In this case, we use a qualitative color scale. Such a scale contains a finite set of specific colors that are chosen to look clearly distinct from each other while also being equivalent to each other. The second condition requires that no one color should stand out relative to the others. And, the colors should not create the impression of an order, as would be the case with a sequence of colors that gets excessively lighter. Such colors would create an apparent order among the items being colored, which by definition have no order. The ggplot2 hue scale shown in this slide is the default qualitative scale in the widely used plotting software ggplot2. Color to represent data values. Color can also be used to represent data values, such as income, temperature, or speed. In this case, we use a sequential color scale. Such a scale contains a sequence of colors that clearly indicate, a, which values are larger or smaller than which other ones, and b, how distant two specific values are from each other. The second point implies that the color scale needs to be perceived to vary uniformly across its entire range. Sequential scales can be based on a single hue, for example from dark blue to light blue, or on multiple hues, for example, from dark red to light yellow. Multi-hue scales tend to follow color gradients that can be seen in the natural world, such as dark red, green, or blue to light yellow, or dark purple to light green. The reverse, for example dark yellow to light blue, looks unnatural and doesn't make a useful sequential scale. The heat scale shown in this figure is a multi-hue scale that varies from dark red to light yellow. Color as a tool to highlight. Color can also be an effective tool to highlight specific elements in the data. There may be specific categories or values in the dataset that carry key information about the story we want to tell, and we can strengthen the story by emphasizing the relevant figure elements to the reader. An easy way to achieve this emphasis is to color these figure elements in a color or set of colors that vividly stand out against the rest of the figure. This effect can be achieved with accent color scales, which are color scales that contain both a set of subdued colors and a matching set of stronger, darker, and/or more saturated colors. An example of accent color scales is shown in this slide, with 4 base colors, gray values, and 3 accent colors. Data visualization is the graphical representation of information and data. By using visual elements like charts, graphs, and maps, data visualization tools provide an accessible way to see and understand trends, outliers, and patterns in data. In the world of big data, data visualization tools and technologies are essential to analyze massive amounts of information and make data-driven decisions. In the introductory learning unit, it was highlighted why visualization is a useful medium for examining, understanding, and transmitting information. The different kinds of visualizations were presented and the main differences with the infographic illustrations were mentioned. Also, some fundamental concepts of data visualization were presented, such as the quantifiable features formerly referred as aesthetics, the coordinate system determining where data values are located, and the various color scales. This is the end of the introduction learning unit. Thanks for watching this video.